Okay, it should be recording right now. All right, so let's start a review for exam 2. So exam 2 is going to follow the exact same similar format as the exam 1, where you guys are going to have 25 questions. The idea is usually what I recommend people, especially for project 2, I say do not depend on the formula sheet. Formula sheet for project 1 was extremely useful. Formula sheet for project 2 is shit. Formula, and I call it project for exam. For exam 1 was very useful. For exam 2 is complete garbage. For exam 3, it's kind of useful again. So it's kind of like a woo. That's your grade. That's your grade going woo. So definitely keep that in mind. Make sure that a lot of the concepts and a lot of the how to do something, you actually know how to do them. I do recommend that you do on your calculator as much as you can. It's going to really help you a lot, because if you have something, if you have to do something like nonlinear Newton-Raphson, or if you have to calculate the residual of a linear system of equation, so A times X minus B, you can actually write that on the calculator. If you don't have, you're not supposed to have an extra computer or anything like that, but if you're very, like if it was me, I would just have Octave with me open and I would just do the matrices like that. But because I type fast, if you're more comfortable with a calculator, something like a TI-84, something like a TI-36X Pro, definitely not a TI-30X. That's like a kill yourself calculator. You want something that is capable of doing matrices. But if you have those calculators, I think you can define up to a 3x3, and you can define, I think, up to 3 either matrices or vectors. So then you can, if you know how to insert them, you can just do A times B minus C, where it's your matrix times the solution minus the right-hand side vector. And that will give you a vector. That will give you the residual vector. So definitely, if you can do as much as you can with the calculator, even though we say, oh, you want to show your work in the all of that, that's just monkey work at that point, because it's just like calculator and matrices and all of that. So you want to save as much time as you can. In the same idea, questions is 25 questions. So question 15 to question 20 are going to be Gauss-Seidel and or Jacobi method. So Gauss-Seidel and Jacobi method are very similar. So you're going to have Gauss-Seidel or Jacobi, and then question 20 to 25 will be nonlinear Newton-Raphson. So my advice, usually what I tell people is, if you are someone who suffers from time, and you know, like time management on a quiz, you get, or an exam, you get so caught up in a question, I will advise that you start with questions 15 and onwards, because then if you know how to do Gauss-Seidel, or if you know how to do Jacobi, it's a matter of just sitting down and kind of like go through the process. If you work one of those problems by yourself, it's kind of like a process. It's the same thing as when we were doing linear Newton-Raphson and bisection. It's like, oh, we start from here. At every single iteration, make sure you calculate your residual and your iterative convergence, and then move to the next iteration, and then move to the next iteration. So if you do the process, you will know how to answer those 5 questions. Very important that you know how to calculate norms. I will get into that in a second, but very important, we do not care if we ask you for a residual vector or an iterative convergence vector. We don't care about the vector itself. We care about the norm of the vector. And very often we use infinity norm. I don't think we're going to ask you for L2 norm. So as long as you know how to do L infinity norm of both a matrix and a vector, they're different. So matrix and a vector, it's different how you calculate the L infinity norm, but you have to make sure that you know how to calculate it. I think that's it. Make sure for nonlinear Newton-Raphson, and again, I will get to that in a second, but for nonlinear Newton-Raphson, the equation for calculating the residual changes. I was on a quiz in class, and people always think, oh yeah, it's still a matrix or it's still a vector. And this exam, I guess I can start diving on the exam, but the exam 2 or material for exam 2 deals with 2 things. So the idea is there are 2 major topics. So let me say, whoa, that's the eraser. I'm going to say there are 2 major topics. So what are those 2 major topics? We want to know how to solve. So I'm going to say over here, 1 is going to be solve, and I'm going to put it in red, linear systems of equations. So we want to solve the linear system of equations. And then there is also number 2. So the 2 major topics. This is from the end of exam 1 up to the beginning of exam 3 material. So we solve linear system of equations, and then we also want to solve, and here's the tricky part, nonlinear. So nonlinear system of equation. Now, without getting into all the details of what method do we use and anything, what is important to know is that, for example, here in the beginning, I'm going to say for solving linear system of equations, we use things like, we use Gauss elimination. We use Gauss elimination. We use Jacobi, the Jacobi method. We use Gauss-Seidel. So anything that can be represented as an AX equals B. That can only happen for linear system of equations. Nonlinear system of equations, on the other hand, even though we represent them a vector, it's a completely different ways of solving it. And that's why we apply what is known as nonlinear Newton-Raphson. Now, you guys cover more than this in the class, but this is like what is relevant to the exam, because you guys did a steepest descent and the French guy that I have no idea how to pronounce his name, and then nonlinear Newton-Raphson. So you guys saw like 3 different ways of solving it. And I think the French guy is like the combination of Newton-Raphson and steepest descent. So there are different algorithms, but these are the ones that are prevalent to the class. And so that's what I wanted to start. There are 2 major topics. How do we solve systems of linear equations and nonlinear equations? So even though you can call something a system, and it doesn't have to necessarily be something that you can represent as a matrix. We don't write these things as a matrix, but we use matrices and vectors for everything because we're talking about the multidimensional domain. Okay, so linear systems. So I think that it's very important, and I'm going to start here with linear systems. So linear systems of equations. So let's start with that one. And the first thing that I'm going to say, or probably the most obvious, is that they can be written. It's written with 1 T or 2 T's. I always forget. 2, okay. They can be written as A times X equals B. Also, remember that this is the same thing. He likes to show you guys 2 different, or his way of writing matrices and vectors. So you can write a matrix like this times a vector. You can use like a squiggly line at the bottom. Those 2 mean the same exact thing. It just depends what kind of notation do you want to use. So linear system of equations are the ones that we can write like this. I'm not going to go into the details of how we can write them like this or why. It's just, if you don't know, it's because every single unknown, every single variable, the highest power is 1, and you don't multiply 2 variables together. Like you don't see something like 1x plus 2y equals another constant. You can move things around and put it in the form y equals mx plus b, like the equation of a line. So that's a linear function. If you have something like x times y plus 2 equals something else, that's a nonlinear function because you have 2 variables multiplying each other. Or if you have something like x squared, that is not a linear function. So be careful with that. Only linear functions are the ones that can be written in the form ax equals b. So things that are important to know, and I'm going to try to continue using red here on the little side. I'm going to say if given matrix A, and calculating, you may be given this though, and calculating A inverse. So the inverse, you don't have to necessarily know how to calculate it. I think that Calculating the inverse of a 3 by 3 is a pain in the ass. And I think that for all those cases, we're going to give you guys the inverse. So we will give you like A and A inverse. But I just say and calculating because if it's a 2 by 2 and we just want to be complete assholes and we're like, no, we're not going to give it to you, then you have to calculate it yourself, which is not very difficult. Again, you have a calculator, you can use that. But if you're given matrix A, you will always be given the matrix. You're all given the matrix A and you're given and there exists an inverse, which we'll get that in a second, but we calculate that inverse, then, let me say, then the conditioning number is, and sorry if I'm typing very slow, I'm having a difficult time. I don't know, I feel so uncomfortable in here. The conditioning number, it can be defined as you have your matrix A. I'm gonna write it like this. The infinity norm of your matrix A and the infinity norm of your matrix inverse. So if you take your matrix A, if we give you the matrix A and you either calculate the inverse of that matrix A, if it's like something like a 3 by 3, or we give it to you, what you're going to do is to find out the conditioning number. You're going to take your matrix A and you're going to find the infinity norm of that matrix. It's not a vector. So the way you go about it changes. But you take the matrix A, you calculate the infinity norm of the matrix, you take the inverse of the matrix A, and you calculate the infinity norm of that inverse matrix, and you multiply those two results. That will give you the conditioning number. So that's why I say it's very important that you know how to calculate the infinity norm for a vector and for a matrix, because the way you go about it changes. It's not the same thing. It's not, oh, I'll do absolute value of this, pick the highest one. No, like you actually do a reduction of the dimension. You turn it from a matrix to a vector, and then from the vector you do the traditional way. Uh, so this is important. If given matrix A and calculated an inverse, then the conditioning number, it's defined that way. And then I'm gonna say what does it represent? So what does this guy represent when we're talking about the conditioning number? And what it's important to know about the conditioning number is if, I'm just going to say if K of A, so the conditioning number, is small. If the conditioning number is small, for example, then we can say it's an accurate solution. Now, even though I'm only talking about solution here, because I don't want to, a lot of things that I teach or a lot of things that I say during these reviews, a lot of things are from memory. I don't really go over material before I talk about this because I rely on my PTSD from this class. And if the conditioning number is small, I know that it will yield accurate solutions, but there is a relationship between conditioning number and residual, like yielding big residuals or small residuals depending on the conditioning number. So this is definitely something that you want to go back on your note and look at. What is like the relationship between conditioning numbers and residual? Like if it's a small conditioning number, what do we mean by small? Because you can have a conditioning number that is like 10 to the 3, and that's not considered big. It's not considered huge. It's considered relatively small. So conditioning number is not like the traditional residuals when we want to see very small numbers, 10 to the negative 17 or something like that. Conditioning number is a very normal, I will say it oscillates between very normal values. So if you go back to your note, look at what values of conditioning number are considered big, what values of conditioning number are considered small, and how does that influence the residual from our calculation and our solutions. Can we it's a small conditioning number, does that mean that we obtain accurate solutions, or is the combination of all three? Because you may have conceptual questions that ask you in that aspect. But conditioning number, definitely make sure you know how to calculate it. Make sure what does it represent for your system. So moving away from that. So yes, if I wrote it here right now, if the value of your conditioning number is small, we say that it will indicate accurate solutions, which is something that I say. If the resultant is big, it's a huge number for your conditioning number, then you can assume the positive, the opposite, like your solutions are not accurate. So that's why you cannot trust them in a sense. So let me move down a little bit. All right, so I already talked about that. Should you, oh, this one is very important. So, and this one is one that I want you guys to kind of like participate. So if I'm given A, I'm gonna say, how do I know if I should implement, and there is the favorite word of a lot of people, pivoting. And I'm gonna say either partial or full. So if I am given, whoa, what happened to this? Did you die? Oh, there you go. Just lie. Okay. So if I'm given a matrix A and the matrix is already defined, I can look at it. It can be a 3 by 2, a 3 by 3, it can be a 2 by 2. How do I know if I should implement any form of pivoting, either partial or full pivoting? Hmm? Yeah, you have to check if it's diagonally dominant. So I'm gonna say, what happens to my computer? Whoa, whoa, whoa. We're having a party here.
So if it's not, then you do partial.
Yeah.
Pardon me? So if it's not diagonally dominant, you do partial.
Yes, exactly. You can either do partial or you can do full pivoting. But if you whether to not, you have to do pivoting at all. You have to check if the matrix is diagonally dominant, because that's the idea. We implement pivoting in order to make a matrix that is not diagonally dominant, diagonally dominant. And why do we do that? Why do we want a matrix to be diagonally dominant? You guarantee that you will converge. You guarantee convergence. So that's why very important. That's a question on the exam, by the way. Let's see if my screen decides to stop doing techno dance over here. Uh, anyway, so we talk about pivoting. You have to make sure, also you have to deal with my accent. So I guess that's not as useful, but want to definitely make sure you know how to do Gauss elimination. No, absolutely know how to do Gauss elimination. And when I mean Gauss elimination is note how to do the process of, you start with a matrix A, you do elementary row operations. That's very important that you don't skip that step. The process of elementary row operations, and I think there is a bunch of like calculators online that will, you give it the matrix and it will give it to you in the upper triangular form. That's, you take a matrix, and you do you do elementary row operations so that you take that matrix and you put it in the upper triangular form. This is very important because we're gonna, just like in the quiz for project 3, we're gonna ask you about a specific index, about a specific thing. It's like, for example, oh, in your upper triangular matrix A, what is the A22? Like second row, second column of the triangulated one, not the original one. So definitely make sure you know how to do that. Now, if you want to use any form of like, oh, algorithm or anything that does it for you, and then you have a boom, or if you figure out how to do it with your calculator, I think the calculator does the row reduce echelon form or something like, or echelon form. You can mention it both ways, but I don't believe that that's exactly the same as the upper triangular form. It's very similar, but I don't think they're the same. But if you want to implement the elementary row operations, you don't want to do it by hand, find a way around it to make it easier. But Gauss elimination is an exact method. So I don't think that they're going to ask you for the solution of the system. If they do, you can just do A inverse times B, like matrix A inverse times B, and that will give you the solution of the vector X. Because it's a direct method, so there's no form of iteration or anything. But definitely make sure that you know how to take matrix A, do elementary row operations so that you transform it into the upper triangular form. And remember, you have an upper triangular A and an upper triangular B, because anything you do to one side of the equations affect the other side. So because we will ask you for one component of the triangulated A and one component of the triangulated B, we will ask you for the solution, and then we will ask you, how do you go from here? How will you solve it? And the way that you solve it is, once you have your matrix in the upper triangular form, you solve it by doing back substitution. Not forward substitution, but back substitution. So, but very important that you know how to do it by hand. A and T, blah, blah, blah. Okay, we will also ask for the solution vector. You don't have to do back substitution. It's an exact method, so you can just solve it A inverse times B, because they will ask you for the solution vector after performing the Gauss elimination. Just do A inverse times B, and it will give you the same thing. Um, for the linear system of equation, very important that you know how to calculate the residual and the iterative convergence. Residual for the linear system of equation. That's why it's very important. The equation for calculating the residual of a linear system of equation, it's matrix A times vector X at whatever current iteration they want to give you, or whatever vector, they will give you a vector X. Like they will say, calculate the residual at this iteration, and they will give you a vector X. So you do A times X minus B. The multiplication minus the B will give you a vector. That is your residual vector. And again, they never want the vector. For a residual or for iterative convergence, they never want the vector. They want the norm. So you have to calculate the infinity norm of that. The same thing with iterative convergence. Iterative convergence, it's the same for like this whole exam. It's just the new vector minus the previous vector of solution. So this current X minus the previous X. So vector minus a vector, they have the same dimensions. You get a vector at the end.
Do you know where there's an example of that?
Of what?
Of the residual, just the step by step.
I can send you one. I don't think, yeah. If you take any matrix A, any vector B, and any solution X, just do AX minus B, and that will give you a vector. And that's your residual vector. That's what we are doing in the project. We just did it in project 4. If you go into the GS SOR code, the part where it says calculate the residual, it says A times X minus B.
Okay.
And we did the norm of that after.
Okay.
But yeah, definitely make sure you know how to do that. And as always, we want the norm of it. If you are, this one is a very, very, very particular question. If you're using Gauss elimination, and I said that it's a direct method, if you're using Gauss elimination, and I want to ask you, if you want to solve a system by doing a linear system by doing Gauss elimination, and I ask you how many floating point operations, AKA flops, how many floating point operations it will take for you to arrive to a solution. It will take, that's the big O notation that we often use. It will take the size of the matrix on one side, so n is the size. If you have a square matrix, it's an n by n. You're gonna take n and you're gonna cube it. So it's n times n times n. So if I give you a 3 by 3 and I ask you how many floating point operations will it take for it to converge, 3 times 3 times 3, that's going to be 27. I hope. So what does the determinant of a matrix tell you? That's a very good question. And I'm actually curious because it's interesting because I feel like engineers, we know how to use math. We know jack shit about what it means. Like the actual definition of things. So determinants are very important. You guys know how to calculate the determinant of a 2 by 2. And so what does the determinant tell you, first of all? Like not conceptually or anything like that. It's just there is something that is very important that the determinant can tell you whether it exists or not.
So if the solution exists, you're checking to see if it's
I don't think so, no. Well, if the determinant is, what happens if a determinant is 0? You say that you cannot solve the system, right? But why? It's because the inverse doesn't exist. Yeah. So if a determinant is 0, there is no such, you cannot calculate the inverse of a matrix. And you need the inverse of a matrix to calculate a solution. Hence why we use X equals A inverse times B. Because it's the inverse of a matrix. And also because when you calculate the inverse, for example, in a 2 by 2, when you calculate the inverse, you do 1 over the determinant of that matrix, multiply times, like, I think it's like the B times C or whatever thing. Like there's so many ways of solving that, but you're dividing by 0 in a sense. If the determinant is 0, when you calculate the inverse, you divide by 0. And that's why it's undefined. So that's why we say it doesn't exist. But make sure you know that we calculate the determinant of a matrix to know that there exists an inverse for that matrix, because the inverse is always only 1. So for iterative methods, so we talk about pivoting. When we're talking about direct methods for linear system of equations, when we're talking about direct methods, we're talking about Gauss elimination, for example. We said Oh, pivoting is very important. Pivoting is necessary because we don't know if we have to implement it or not. How do we know if we have to implement it? We'll check if it's diagonally dominant. The same holds for iterative methods. So something like Gauss Seidel and Jacobi. Gauss Seidel and Jacobi, uh, the question will be different, but I can ask you something similar. I say, hey, if I'm implementing any form of Gauss Seidel or Jacobi method, how do I know if I'm actually going to arrive to a solution? You check if it's diagonally dominant. If your matrix, if the matrix that you're given is diagonally dominant. That's how you know whether you can guarantee that one of those two iterative methods will converge. So that's as far as linear system of equations or uh, the direct methods for linear system of equations. For Gauss-Seidel and Jacobi, I'm kind of sad because I really wanted to. So that's the first 15 questions. That covers pretty much everything from the first 15 questions. I will definitely suggest that you know how to calculate eigenvalues, or that at least you know what eigenvalues represent. And there are two instances of this. There's the one that you guys saw in the quiz that is like, oh, if you have a matrix A and you multiply it by a vector that is an eigenvector of the matrix, it doesn't rotate. You obtain the same exact vector, multiply by scaling, by the eigenvalue. So the vector never changes. And I was really excited to talk about this because I feel like matrix multiplication is one of those things that people don't understand. They know how to do them, but they don't know what it means. And that's why eigenvalues are so difficult to understand. But eigenvectors, definitely, you don't have to calculate an eigenvector. Just know what the eigenvalue does to the matrix, like what does it represent. And there is a question that he likes to ask where he says something like, when you're doing the Gauss elimination method, there's something that he goes over the class. I think he goes over it pretty quickly, or most people just don't like see it. And he asks about like something called the iterative matrix. It's like a matrix, and it's something called the iterative matrix. I don't remember exactly, but he says if we're performing the Gauss-Seidel method in this system, you have an ax equals b, and then we arrive to the iterative matrix in the form of, and he defines it as t. I think he defines it as t of Gauss-Seidel, and then he tells you what the eigenvalues are. The reason why he gives you the eigenvalues is you have to look at the eigenvalues and you have to look at the magnitude of those eigenvalues. If the magnitude of those eigenvalues are less than 1, your system will converge. That's another way that you can guarantee convergence if you're doing Gauss-Seidel by looking at the eigenvalues. If the eigenvalues are less than 1 in magnitude, you guarantee convergence. If they're greater than 1 in magnitude, at least one of them, there is no guarantee of convergence. If they give you a number that has a real and an imaginary component, you have to do the magnitude of both. So square root of this one plus this one, like square. So definitely know how to calculate, because again, it's just a vector, real and imaginary. You do the square root of this one square plus this one square. So that will give you, so you can check if they are the magnitude of all the eigenvalues. But again, it's because I think that it's not the eigenvalues of matrix A, it's the eigenvalue of that iterative matrix that he creates, which is it's defined as like T. And I think that that's what you check. But you don't have to do this process by hand. It's a conceptual question. You just have to look at the eigenvalues and be like, yeah, it will converge, or no, it will not converge. So look at the magnitude of the eigenvalues. But Gauss-Seidel and Jacobi, make sure you know how to do them. They're extremely similar. It's just a matter of at what point do you replace the values as you obtain them. Because Jacobi, you wait. Jacobi, if I'm doing the first iteration, I use all of the values from my initial guess vector. I use all of them. And then at the end, I replace them. Gauss-Seidel is different because as soon as you find a value, like let's say I use my initial guess to find x1, the first component of my x solution vector. As soon as you find that one, you don't use x1 ever again. You don't, the one from the initial guess. It's like you never use it because you found a new one, and as soon as you find a new one, that's what you start using. You don't wait till the end of the iteration, till you find all of your solutions. You use it as you go. Jacobi, you wait until the end, and I will elaborate more on this. Um, Again, make sure that you understand how to calculate the residual and the iterative convergence. Gauss-Seidel and Jacobi are both linear applied for linear system of equations. So the residual is matrix A multiplied times vector X minus B. And then the iterative convergence is new vector minus previous vector. But know how to do that and know how to find the norm. We will always ask you for the infinity norm when it comes to vectors and when it comes to residual and iterative convergence vector. And now the final 5 questions are going to be about nonlinear Newton-Raphson. Nonlinear Newton-Raphson is very important. These are for nonlinear system of equations. What does nonlinear system of equation mean? It means that we cannot write it as ax equals b because they're nonlinear. We have nonlinear equations, so we cannot write it like that. That only applies for linear system of equations. So very important that you know how to do this process. Very important that you're very organized when you're doing this process. First thing you want to do is calculate the Jacobian matrix. Calculate the Jacobian matrix and put it in terms of the unknown variables. So if you have whatever equations and you calculate the Jacobian matrix and it's like, oh, this component is 2x1 times x2. This component is 2x1 squared. This component is like, that's perfect. That's what you want because the Jacobian matrix will change at every iteration because the Jacobian matrix depends on the vector x. That's why you have those variables inside of the Jacobian matrix. So at every single iteration, you have to plug in those values. If they say calculate the initial Jacobian, it's take your Jacobian matrix and plug in the values of the x initial guess vector. So it's all part of a process, and I want you guys to get really good at that process because it takes time. And if you're organized, if you define everything and you're very organized on where things are, you're gonna have a beautiful time. If you're very disorganized and you write everything everywhere, it's going to be horrible. And the only change between, or the major change for nonlinear system of equations, if you're trying to find, if you're finding the residual, again, it's not ax minus b because it's not a linear system of equation. The residual you calculate by taking the absolute value of the function vector evaluated at the vector of solutions. So if you think back on exam 1, linear Newton-Raphson, absolute value of the function evaluated at that x, at whatever current x we were looking at. Now it's the same exact thing, but it's with vectors. You're going to take the absolute value of the function. Your vector is a vector of functions. Your function is a vector of functions. So you will plug in all of the values from your x at that current iteration into that vector. The idea is that at the end, you will have a vector. So you're pretty much taking your vector of functions and evaluate it at the current x. Whatever, when I say current x, I mean the vector of x, all of the values that you have. You will plug them in there and then evaluate it and then do the infinity norm of that. Everything that ends up in a vector, we always do an infinity norm. And the iterative convergence is the same thing. A vector, the new vector minus the previous vector, that one doesn't change. But the residual, the equation for the residual is very important that you understand how did it change from linear system of equations to nonlinear system of equations. So definitely know that. And that's going to be the whole exam. Do you guys have any questions? I'm sorry that my tablet decided to die. I don't know if it was the tablet. I think it's probably the cable, honestly. This cable is absolute shit. I absolutely hate doing Gauss elimination, so that's on you. But everything else, I'm happy to show you how to do it. I absolutely despise Gauss elimination. But I guess I can stop the screen share. Are you okay? Should we be concerned?
Oh, no,
I'm just kidding.
Sneezing's not a symptom of COVID.
It's not?
No.
Oh, I guess that's a good thing. Come and sneeze closer. Listen, if you give me an excuse to not be here, I'll be happy. Okay. Again, I'll just re-record this on the, MS Paint. That's actually not a bad idea. I feel like this recording is just going to be me losing brain cells for this shit show. Oh God, this is terrible. Yeah, I'm doing this. It pisses me off. Listen, you're taking fluids with Boosie. Have you ever seen how he fucking handwriting is? It's like, it looks this thick. It's like he goes, oh yeah, we have a fluid, and then he just draws a fucking line that is the size of the screen. Do you think it was any better in person? No, he picked up the fucking, the thickest Sharpie he could find on his way to the classroom, and that's what he will use. And he's like, yeah, how do you guys don't understand this? Like, I don't even fucking know what you're writing. It's not even English at that point. But anyway, you know what? I'm not gonna do this. I'm just gonna tell you guys what to do, and then over the weekend I'll just record it, because I'm like